In this first example, I have a system of nonlinear equations. Technically, one of them is linear, right? This bottom one is linear, but this top one is not. In fact, it's half of a parabola. It's our square root function opening up to the side, up to the right. Okay, and so if I were just to plot the graph of this, just a quick sketch, I don't even need all of the details. I know that y equals root x. Well, the square root of x is our square root function, right? It starts at the origin, goes up to the right, but it's multiplied by 2, so it's kind of stretched out by a factor of 2, which means it's going to be, a little bit wider, I suppose, as a parabola. X minus 3 is a linear function with a slope of 1 and a y-intercept at -3. So -3, and it slopes up at 1. And so it appears that there's going to be 1 point of intersection. Okay. Right, and then from there on, the two graphs diverge away from each other. And because this half parabola ends at the origin here, there's not going to be a second point of intersection. At least that's what I would get if I were thinking about the graph of these equations. And so with systems of nonlinear equations, you can have a linear equation, but they're not both going to be linear. Okay. Okay. So now let's think of a method for solving these. Well, I'm going to go with the substitution method. Okay, and what I'm going to do for substitution is I'm going to substitute one expression for y into the other one. So basically, since the two y's are going to be equal at the intersection point, I'm going to plug in the 2 root x in for the y in the second equation. Sometimes you'll see this in the textbook, you'll see the equations labeled, like we'll call this equation 1 and equation 2, and then they refer back to plug this into equation 1, plug this into equation 2, that sort of thing. So I may even do that as I go, but in this example, it probably isn't that big of a deal. Here, I'm just going to take the 2 root x, plug it in for y in equation 2, so 2 root x equals x minus 3. Now I have a single equation with a single variable. I can solve for x, but solving for x on this one is not real straightforward because it's not a line. I do have to square both sides to get rid of the root. Okay. Now when I square both sides, there's two options here. I could divide out the 2 before squaring, but that creates a fraction on this side. It really isn't that big of a deal. The 2 being a positive number, it doesn't really matter when I square it where that 2 is. So I'm going to go ahead, actually even as a negative number, it wouldn't matter. So I'm just going to go ahead and square both sides as written so that I'm not dealing with fractions. Normally though, you would want to isolate the root before squaring, but in this case it's convenient and it's not going to change things to leave it. So I square both sides, and the left-hand side becomes 4 times x, right? So you square the 2, square the root x. And the right-hand side, well, we have to use the perfect square trinomial formula, right? So you take the first term squared, double their product, which is minus 6x, and then the last term squared is plus 9. So that's our perfect square trinomial, where you could do x minus 3 times x minus 3 and distribute. From here, this is now a polynomial, specifically a quadratic equation, and I can solve that by getting a 0 on one side, and then either factoring or using the quadratic formula, whatever is most convenient. X squared minus 10x plus 9. Now in this one, I notice that 9 has factors that add up to -10, namely -1 and -9. And so this one is going to factor into x minus 1 and x minus 9. And when I set each factor equal to 0, x minus 1 equals 0, x minus 9 equals 0, which makes x equal 1 and x equal 9. Gives me 2 possible solutions. Now the problem with that, remember, we really should have 1 point of intersection here, so we may have an extraneous solution pop out right away. But let's go back through and find solutions, see if we can get a point and solve it. So if I plug in a 1, let's plug it into equation 1 here. up on top. So I use equation 1, I have y equals 2 root 1, right? And 2 root 1 is just 2. So that would give me the ordered pair 1, comma 2, right? X value of 1 and y value of 2. The other point, the 9, if I plug that in up here, again using equation 1, y equals 2 root 9. Of course, root 9 is 3, 2 times 3 is 6. That tells me that 9, comma 6 is on that graph as well. So 1, comma 2, 9, comma 6, if I were to check, right, so these are my two apparent solutions. If I were to check those, check the 1, comma 2, I'm going to check it in the second equation. I already know they're going to work in the first equation because that's how I got the y value, but it's the second equation I need to check it in. And when I check it, the 2 goes in for the y, I get 2. Is that equal to 1 minus 3 if I plug in the x? So y here is 2, x here is 1, and of course those two things are not equal because it says 2 equal negative 2, that's not true. Okay, so that does not check out. I don't need that one then. The other one, just to verify, I get a 6 on the left. Will that equal 9 minus 3 if I plug in the x there? And of course it will. You get 6 equals 6, which does check out. And that tells me then that my solution is the solution set containing 9, comma 6 with the other point here, 1, comma 2 being extraneous. Okay, so again, it is very important to check your answers when you get to the end, because at times you will end up having some extraneous solutions. Generally speaking, that will occur if at some point in the problem you square both sides. That's usually the culprit. Okay, when that occurs, you often, not always, but often get extraneous solutions. It's probably the most common situation, but you can also get extraneous solutions if you end up having to divide by a factor with a variable in it or something. That division process can sometimes create extraneous solutions as well. So there's other things, but be especially careful if you have to square both sides of an equation. That may be the case where you develop an extraneous solution.